In this chapter, we will work on different methods of analysis. And we will cover two main methods. So we will first cover nodal analysis, node meaning point, nodal analysis, and we will use Kirchoff's current law to analyze these systems. So KCL for nodal analysis. And then we will also work on mesh analysis. Mesh, also loop analysis. And in loop analysis, we will cover Kirchoff's voltage law, KVL. And we will cover these two methods in this chapter, and we'll go over a lot of practice problems. Let's first tackle nodal analysis. So if we move over to our desktop here, we're going to look at nodal analysis. Nodal analysis. And this will be our first method of analysis that we will go through. And nodal analysis comes from the word node. And if we take a look at what node means here, if we take a look, node is actually a centering point of component parts. So we're looking at this definition too here, but it can also mean different things depending on the context. But in this case, in this class, we will use a centering point. So we're talking about a single point. Nodal analysis. Okay, so the root word node here, and the steps that we will use for nodal analysis. Step 1 is select a reference node. So we need to look at the circuit. If we look at the circuit, we pick a single node and we say that's 0 volts. So 0 volts. So 0 volts. And sometimes I misspelled this. This is reference. Reference. There we go. Reference node. Let's erase this. Reference node. So that is 0 volts. And what we're looking to do is sometimes we call this the ground. So we draw a symbol like this, or we draw a symbol like this, right? Some sort of reference node that has 0 volts. We say that is 0 volts. And then step 2, we use KCL, Kirchoff's current law. So if you remember, we take a look at a node and we look at the currents coming in and the currents going out. So we analyze that. A lot of times we need to figure out if we have a resistor here, and let's say we have 1 here and 2 here, and we have a resistance R. If we want to figure out the current I, we can use Ohm's law. Ohm's law, remember, is V equals I times R. So what we can do is write the current I is equal to V1 minus V2 divided by R. So this is the voltage across this resistor. V1 minus V2 divided by R is the current here, I. Now remember the order. So this current flows from high to low. So current flows from high to low. So V1 here is higher than V2. Okay? If we think the current is going the other direction, if the current is going this direction, we need a different formula here. In this case, we have V2 is high, so we have V2 minus V1 divided by R. So depending on which direction the current is going, we need to write our formula appropriately. Okay, so this is high and low. So high to low. And we write a bunch of KCL equations. We do KCL at this point, KCL at that point, KCL here, and then we combine all the equations. So the third step is solve equations. So these are the 3 steps to doing nodal analysis. Nodal analysis. Now let's look into doing an example using nodal analysis. An example. So I'm going to draw a quick circuit here. So this resistor is 2 ohms. This resistor is 6 ohms. This resistor is 4 ohms. And this is a current source. And the current source is 5 amps. And this is a current source. And this is 10 amps. And so we want to do nodal analysis on this. Nodal analysis is good when we have current, when we know current here. So we need to first select, step 1, select a reference node. So if we use the bottom here, this whole node as our reference node, our reference. So our reference node, and so we draw a ground, and that is 0 volts. So this node here is 0 volts. Now let's label our other nodes. We have another node here, we have node here, and then we also have another node here. So this node, so I'm going to label those 1 and 2. Okay, so we have our reference. Now let's do KCL for our nodes. So I'm going to do node 1 first off. And let's draw our current. So we have I1, I2, and I3. We can draw the arrows any direction that we want. You can draw them this way or you can draw them this way. It doesn't matter. If you get a negative value, that means it goes the other direction. Okay? So I'm going to draw the current this way. And now let's look at doing our equations. Remember, KCL is in equals out. In equals out. So we have I1 coming in. And then going out, we have I2 plus I3. And we know what I1 is. I1 is 5 amps. So we have 5 equals I2. And what is I2? Well, I2, remember we use Ohm's law. V equals IR. And I is equal to V over R. So I2 is V1 minus V2, high minus low, divided by R, which is our 4 ohms. And then I3 is the same thing. So we go plus V1 minus here, this point. Remember, this is 0 volts, 0 volts. So V1 minus 0 divided by this resistance 2. And here we have our first equation here. And we do not know V1 and we do not know V2. So there are 2 unknowns. 2 unknowns and 1 equation. We cannot solve this equation yet. We have to continue and get 1 more equation. We need 1 more equation. So let's look at node 2 right here. And we will draw our values here. So we have I2 coming in here. And then we have I3, or no, I4, I'm sorry, I4, and I5. And this is I1 here. This is the same. This is the same as this. I1. This is the same. So we do not necessarily need to write that there. And then coming in this way, that is I2. So I2 here. So let's do our equation. In minus out, or in equals out, I'm sorry, in equals out. And we coming in, we have I2, I4, and going out, we have I1 and I5. I1 plus I5. In minus out. I2, remember, is V1 minus V2 divided by 4. And I4 is 10 amps. 10 amps. I1 is 5 amps. 5 amps. This should be equals 5 amps plus I5. And I5 here is V2 minus 0 divided by 6. So that is just V2 over 6. Okay, so here we have 1 more equation. 1 more equation. So now we have a total of 2 equations and 2 unknowns. We do not know V1 and we do not know V2. But we can solve these equations together and then come up with our answer. To solve these equations, we can use this first one, and let's multiply it by 4 to make it easy, to make it a little easier. So that equation becomes 20 equals V1 minus V2 plus 2V1. Okay, so that is equal to 3V1 minus V2. This equation here we can multiply by 12. So we multiply this one by 4, multiply this one by 12, and we get 120 plus 3V1 minus V2 equals 60 plus 2V2. So we have these two equations, and we can simplify those equations more. Solving these two equations, we get V1 is equal to 13.333 volts, and V2 is equal to 20 volts. So that is our answer for the voltages at node 1 and node 2. Now that we've covered the nodal analysis, we will now move on to our second type of analysis called mesh analysis. Mesh analysis, which can also be thought of as a loop analysis. So a loop analysis. Let's go ahead and do this. Move over. And so we're covering mesh analysis, which sometimes we can say this is a loop. Loop, L-O-O-P, loop. And this has similar steps to the nodal analysis. But step 1, we assign currents. So we assign currents I1, I2, I3, I4, I5, so on. We assign those currents. And in nodal analysis, we use KCL, Kirchoff's current law. In mesh analysis, we will use KVL, Kirchoff's voltage law. In addition, we'll combine that with Ohm's law. So remember that the voltage is equal to I times R. So we will be combining KVL with Ohm's law. And then from there, we solve equations. Okay, so let's do a quick example of how to do this mesh analysis, this loop analysis. Let's keep going. I'm going to draw a quick circuit here. We have a voltage source. And then we have another resistor over here and a voltage source over here. So we have V1 as our voltage source here and V2 as our voltage source on that side. And we have R1, we can call this R2 and R3. So the first thing we need to do in our steps is assign currents. So I'm going to assign currents. I'm going to draw things clockwise. So we're going to call this I1, and then we're going to have another current here, I2. And once we do that, we now perform KVL, Kirchoff's voltage law. So we will be adding voltages around this circle. Okay. So if we add voltages around this circle, how do we do that? Well, let's start here and we'll go up this way. If we go up this way, I'm going to say that's negative V1 plus I1, that's I1 times R1. So we're looking at the voltages, that's V1. This one is I1 times R1. And then going back down this way, that is plus I1 minus I2, because this resistor has I1 and I2. So I1 minus I2 times R3. And that should equal to 0. Now, a lot of you may ask, why negative V1? If we're going this way, why negative V1? So why negative or positive, right? Why? We want these to have separate signs. So if this is positive, this needs to be negative. Okay? And if this is positive, this needs to be negative. So it is just our choice to pick this method where if we go this direction, that is negative, from negative to positive, we call that negative. And we call the voltage drop from positive to negative, we call that positive here. But it is our choice. We just need to be consistent. We need to say the same. Okay? And now we can go and do this second loop here. So I'm going to start here. And moving up this way, we have I2 minus I1 times R3. And then going this way, we have plus I2 times R2. And coming down this way, this time we go from positive to negative. Over here, we were negative to positive. So positive to negative plus V2 equals 0. Now, if we know the resistance and we know the voltages at the voltage source, we can then solve these two equations here, because we have two equations. So, two equations. And we have two unknowns, I2 and I1. So we would have two unknowns. So this means we can solve. We can solve that problem. Now let's look at a few special cases. So special cases. For example, when we do nodal analysis, we do KCL. But what happens if there is a voltage source and we want to do nodal analysis? So let's take a look at an example. Let's see. Okay, I'm going to draw a circuit which has a voltage source here. I'm going to move this down. here. Okay. And one more resistor up here. Now, this one is 2 ohms. This one is 4 ohms. This resistor is 8 ohms. And this resistor is 6 ohms. This voltage source is 5 volts. And this voltage source is 10 volts. So remember, when we do nodal analysis, we first pick a reference node. And the reference here I'm going to use is here. So that is 0 volts at the bottom. And we have our nodes 1, 2, and 3 over here. So nodes 1, 2, and 3. So how do we do KCL? Remember, C means current. Current. How do we do KCL? Current. How do we do KCL at node 1? It's difficult to do. So what we need to do is come up with some methods. So if a voltage source is connected to a reference node, we then just say V1 is equal to 10 volts. If this is 0, 1 must be 10 volts. And we don't need to worry about that. Now, in between 2 and 3, we have a voltage source. So we need to figure out, how do we do this? How do we do this? So I'm going to draw current here because we're doing KCL. So we have here, we'll call this I1 going into 2. We have I2. And we have, let's say, I4 and I3 over here, I3. We do not know the current across a voltage source. We cannot solve this. So we need to think of a new method. And the method we use is called Supernode. So many of you know Superman. And what we'll be talking about here is a supernode. 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 So supernode. And what we'll do is then combine these two nodes together. So we combine those nodes. And by doing that, we can then use KCL. So we then put 2 and 3 together. 2 and 3 together. Okay, so coming into 2 and 3, we do n equals out. So coming in, we have I1 and I4 is equal to out, which is I2, plus I3. So this is a supernode. So we can still do KCL, but we need to create a supernode. And then I1 is V1 minus V2 divided by 2 ohms plus I4. I4, let's go up. I4 is equal to V1 minus V3. V1 minus V3 divided by 4. And then we have I2, which is V2 minus 0, I guess 0, divided by 8. And then I3 is V3 divided by 6. So this is our equation for the supernode. Now we do know that V1 is 10. So we can change V1, right? V1 over here we said was 10. So we can change V1 to 10. And 10. And there we have a way to do KCL with a voltage source right here. So to finish this up, we have one equation, and we have 2 unknowns. So we have one equation and 2 unknowns. How do we solve this? How do we solve this? Well, we need one more equation. We need one more equation. And what is that equation? Well, it can be V2 is equal to V3 plus 5 volts. So this is our last equation here. So now we have two equations and 2 unknowns. We can now solve this problem. So now solving these equations, we've already figured out that V1 is equal to 10 volts. V2 is equal to 9.2 volts, which then V3 is equal to 4.2 volts. So that is the solution to this problem, and all the nodes, all the voltages at all of the nodes 1, 2, and 3. 10, 9.2, 4.2. Let's consider another special case where we have mesh analysis, but we have a current source. So a special case, we have mesh analysis with a current source. Mesh analysis with a current source. So I'm going to draw a quick circuit here. So we have a voltage source here, resistor, another resistor, and then we have a current source, resistor, and a resistor. Okay, so this is 20 volts. Up here is 6 ohms. Over here we have 10 ohms. And we have 4 ohms here and 2 ohms. And this current source is 6 amps. Now we want to do mesh analysis on this. So we will first draw our loops, which we have I1 and I2. Now, if you take a look at this, if we do KVL, Kirchoff's voltage law, what is the voltage across this current source? It's difficult. We do not know the voltage across this current source. So how do we solve this? Well, what we do is we create a super mesh. So let's go. So we had super nodes, and now we are creating a super mesh. Super mesh. So I'm going to copy this circuit. Let's go down here and we'll paste the circuit. So what we do here is exclude this middle section. So we take this and we exclude it. So and we go all the way around the outside. So we use the big loop here. So let's do that. So I'm going to start here, and we have -20 up to here, and then we have plus I1 times 6. And then instead of going down this way, we go over this way, and we go plus I2 times 10. And then down this way, that's I2 times 4. And then we go back to the start. So that should all be equal to 0. Now we have one equation and two unknowns. So we need one more equation. Well, we get that equation from right here. We say that I2 minus I1 equals 6 because we know the current here. We know that I2 going this direction minus I1 equals 6. So with these two equations, we can then solve this problem. And it comes out, let's take a look. It looks like I1 is equal to -3.2 amps. And I2 is equal to 2.8 amps. So I1 is actually going the opposite direction and I2 is going this direction. So this is our solution for this problem. And this is a special case when we're using mesh analysis with current sources. We need to use super meshes.